Tonight we have with us Ed Murphy from UVA. He's an astronomy professor out there. He's also in charge of the night events at the McCormick Observatory out there. And if you go to their website, you will notice that 2 nights of the month they do have public nights at the McCormick Observatory out there at UVA, and it is a nice opportunity. So please join me in welcoming Ed Murphy.
Thank you very much, and I'd really like to thank the JLab for having me out here tonight. It's a great thing that the Hampton area has such a fantastic science education and outreach group that you have here at JLab, because they just do wonderful stuff. I was here this past summer working with them on a workshop for teachers, and so lots of things go on here that are just really fantastic. But I thought what we would talk about tonight is the origin of the elements, and the fact that everything around us is made of atoms. We all learn in elementary school that the atom is sort of the basic building block of matter. You're made of atoms. I'm made of atoms. This table up here is made of atoms. And the question is, where did these atoms come from? And in particular, there's a couple atoms that I think are especially important to talk about, and one of those is gold. We all carry a little piece of gold with us wherever we go. Or I should say the vast majority of us. So for many of us, it's our rings that we wear. If you're wearing a pair of glasses that have gold rims, there's probably a little bit of gold plating on those. You might be wearing an earring that has some gold in it. If you're not convinced that you have any gold jewelry on, then you might be carrying gold if you're carrying a cell phone, because gold is an excellent conductor of electricity, and it's contained in almost all modern electronics. And so you're carrying a little bit of gold in there. If you don't have any jewelry and a cell phone with you, you might not be carrying any gold, but then you're likely carrying some mercury with you. If you've breathed air in the last day, and I see everybody here has, then you've got some mercury inside of you. It comes from, in many cases, coal-fired power plants that are further west from us. And as we burn that coal, it releases mercury into the air, which ends up landing on our food and our water. So where do these heavy elements come from on the periodic table? So what we're going to talk about tonight is the origin of gold, element number 79 right there. Right next to it is element number 80, mercury, on the periodic table. But I also want to talk about some elements that are a little more personally interesting to us. And those are the elements that you are made of. And the first question I have for the audience tonight is, what are you mostly made of? Water. Most people are made of mostly water. The vast majority of the mass in our body is water. What element is water mostly made of? You think hydrogen. So you'll remember the chemical formula for water is H2O. That's 2 hydrogen atoms and an oxygen atom. So for most people would say that you're made mostly of hydrogen, because if you're mostly water and there's 2 hydrogen atoms and 1 oxygen atom in water, you'd say you're mostly made of hydrogen. But the thing is, astronomers, and in fact most scientists, think a little bit differently, because we think about the amount of mass that goes into making an element and not the number of atoms of that element. So if you look at those periodic tables that you could have picked up on the way coming in, you'll notice that hydrogen has an atomic mass of 1. So those 2 hydrogen atoms in water have a total atomic mass of 2. Oxygen, on the other hand, has an atomic mass of 16. And so by mass, you are mostly made of oxygen. What about this room? What is this room mostly made of? What's the most common element in this room, do you think? It's a little bit tougher one, but if you think about the walls for a second, because those are probably some of the most massive things in here, I'm going to guess the walls are mostly made of concrete. Concrete is in large part made of sand. Sand is silicon dioxide. And silicon dioxide is a silicon atom and 2 oxygen atoms. The silicon atom has a mass of 28. The 2 oxygen atoms have a mass of 32. So it turns out the walls as well are mostly made of oxygen. It turns out that oxygen is probably the most common element in this room by mass. It's certainly the most common element in you. And many people find that surprising. We often think when we study astronomy that oxygen is one of the rarer things that's out there. But in fact, oxygen makes up about 65% of your body. After oxygen, carbon is the next largest thing, and then hydrogen, a little less than 10%, nitrogen about 3%, and then all those other things make up just a couple percent down here, calcium, phosphorus, potassium, and they make up just a few percent of a human body. So you're mostly made of oxygen. something that we often think of as being rare, but in fact, as we will find out, is quite common in the universe. Astronomers not only know what you are made of, but we can tell what things in space are made of, even things that we have never visited and things that we are not likely to ever visit. Take this star cluster, for example. This is a newborn cluster of stars, young, hot blue stars right here that have just been born. This is the cloud of gas and dust from which they were born. Astronomers can analyze the light from these stars and the gas around them, and we can tell what these stars are made of, even though, with our current technology, it would take us millions of years to get to these stars. And the thing is, even if our children develop spacecraft that can go 10 times faster than our current spacecraft, it will still take them millions of years to get to this cluster of stars. If their grandchildren do a factor of 100 better than that, it will still take hundreds of thousands of years to get out to this cluster of stars. We are never, not in the next 1,000 years or longer, going to sample these stars. Nevertheless, astronomers can tell you exactly what these stars are made of. And in fact, they're 74% hydrogen, 25% helium, and everything else is 1%. So all the oxygen, the nitrogen, the carbon, the iron, the nickel, the gold, everything, all those elements are 1%, and the stars are 74% hydrogen, 25% helium. Turns out that's the same composition as our sun. 74% hydrogen, 25% helium, and 1% everything else. And astronomers determine what distant things are made of by breaking the light of those objects down into its component colors. We know that if you take white light and pass white light through a prism, you get a whole spectrum of colors. What scientists discovered back in the 1800s is if you take special elements, particular elements, and you excite them to glow, either by heating them up or running electricity through them, when they glow, they give off only particular colors of light. So if you make hydrogen glow, for example, hydrogen gives off a particular color of red light, a particular color of blue-green light, and two blue lines. Helium, if you excite helium to glow, gives off particular colors of light. And you'll notice the colors that helium gives off are different than the colors that hydrogen gives off. You can think of them as a fingerprint or a barcode. Each element in the universe glows with its own particular set of colors. And all hydrogen atoms, regardless of whether they're on Earth or in deep space, glow with these colors, but only hydrogen glows with those particular colors. So when we're faced with a distant object and we want to know what it's made of, we can take the light from that object, break it into its component colors, and analyze the specific colors that we see and use those to determine what the object is made of. We can do the same thing for our sun, for example. This is a spectrum of our sun, and when we break our sun's light down, we get the full rainbow here, but now we see particular colors are missing in the spectrum. And those particular colors that are missing happen to correspond to, in this case, this red line right here happens to correspond to hydrogen atoms in the atmosphere of our sun that are absorbing that particular color of red light. That red color right there that's being absorbed by the atmosphere of our sun is the same as that red color right there. This blue-green color right here is the same as that one right there. So these lines happen to come from hydrogen atoms in our sun. And astronomers can determine the composition of objects using a variety of different telescopes. Telescopes like the Large Binocular Telescope, which is located on Mount Graham, a couple hours northeast of Tucson, Arizona. I bring this picture up just to mention to people that the University of Virginia is a partner in this telescope. It's the largest telescope in the world on a single mount, and the people of Virginia own a share of this telescope. And the University of Virginia in particular has built a spectrograph, one of these devices for breaking light into its component colors that's used on that telescope. But we can also use other telescopes like the Hubble Space Telescope, and in particular one that I've worked on is the Far Ultraviolet Spectroscopic Explorer. The name tells you everything you need to know. It looks at ultraviolet light, not visible light that we can see with our eyes. Spectroscopic means that it breaks the light into its component colors. And Explorer means that it was a small satellite mission, not one of the big flagship missions like Hubble, but a smaller telescope mission. But we can not only use visible light and infrared light and ultraviolet light, we can even use radio waves to determine what things are made of. Just a few hours west of Charlottesville, so probably about 5 hours west of us here in Green Bank, West Virginia, is the world's largest fully steerable radio telescope. And this radio telescope picks up radio waves from space, and different molecules in space emit different radio waves, including water, for that matter. And we can use radio telescopes like this to trace the distribution of the different atoms through our galaxy and through the universe. So let's go back to the periodic table of elements for a few minutes. And I should mention that I took this periodic table of elements from the JLab webpage. There's a really nice It's Elemental page where you can click on each of the elements and get information about each of the elements. And so you should visit that webpage after the talk tonight. But there's a couple things I'd like to tell you about the periodic table of elements. And maybe the most amazing thing I can tell you about the periodic table of elements, and it's really quite a remarkable thing to be able to say. The periodic table of elements is not just the elements that we know of. It is all the elements that things can be made of in the universe. There is nothing that stuff can be made of that is not on our periodic table of elements. And that's an amazing thing to be able to say, that if there's something in the universe and it's made of matter, it is on our periodic table of elements. And so it's worth explaining why that is for a few seconds to try and justify that statement. It often comes up, for example, when people talk about UFOs. They say if a UFO landed, we would know it wasn't from this world because it would be made of stuff that we don't have on our periodic table of elements. And the answer is if it's made of matter, it'll be made of stuff that's on our periodic table. It has to, because it turns out there's nothing missing off our periodic table. The first thing to know about the periodic table is each element has a number up there. So hydrogen is element number 1, helium is 2, lithium is 3, beryllium 4, boron 5, on and on up the periodic table of elements. That number tells us the number of protons inside the nucleus. There are 3 basic building blocks of matter. There are protons with a positive charge, neutrons with no charge, and they're contained in the nucleus of the atom. And then there are the negatively charged electrons that orbit around the atom. And they orbit at quite a distance away from the nucleus. The nucleus is remarkably small. The best way to think about the nucleus is about the size of a pea in the middle of a football field. So if you imagine the size of a football field with the electrons out here representing the edge of the football field, then the nucleus is about the size of a pea down there at the center of the football field. So the nucleus is very small compared to the distribution of atoms. The different elements on the periodic table have different numbers of protons. So we mentioned before that hydrogen was element 1, and it's element 1 because down in its nucleus, deep down at the center, it has 1 positively charged proton, and which means it also has 1 negatively charged electron orbiting around it. Helium is element number 2 on the periodic table. Its atomic number is 2 because it has 2 positively charged protons. Regular helium also has 2 neutrons, and so it has an atomic mass of 4, but its atomic number is 2. Carbon has atomic number 6 because there are 6 positively charged protons down there. So if we look back at the periodic table of elements, the element number tells us the number of protons. And so we have 1 proton, 2 protons, 3 protons, 4, 5, 6, 7, 8. As you go down the periodic table of elements, you'll see that there are no numbers missing from the periodic table. So for example, let me pick this, 41, 42, 43, 44, 45. Each number is represented on the periodic table. And the thing about protons is they don't come in halves. There's no such thing as 45 and a half protons. You either have 44 protons or 45 protons. You don't have something in between. And if you look carefully at the periodic table, you will see that there are no numbers missing on the table. We have discovered every element there is on the periodic table. I'll talk about these big ones in a second. Now, it's important to say that that has not always been true. When the periodic table was first invented, there were holes in the periodic table. This is the father of our modern periodic table, Mendeleev. And Mendeleev, when he put together the first version of the periodic table, he organized it in rows instead of columns. But the important thing is you'll notice that there were some question marks here. He understood that the periodic table was telling us something about the way matter is put together. And it wasn't just a convenient way for humans to organize all the different elements. It really was telling us something about the structure of the atoms. And what he discovered was holes in the periodic table. And these holes corresponded to elements that hadn't yet been discovered. And when I told you about elements 42, 43, 44 here on the periodic table, I didn't pick those by random. Element number 43 is a beautiful example. It's called technetium. There used to be, until the 1920s, a hole in our periodic table. There was no technetium on the periodic table. And that's because there's no stable version of technetium. Every version of technetium is radioactive and it decays into something else. If you build, and we can do it today, we can make technetium today. If you make it today, the most common version disappears within a few days. It's highly radioactive and it disappears within just a few days. If you look in the rocks on the surface of the Earth, which are hundreds of millions or billions of years old, if there was any technetium in there, it long ago decayed and disappeared. So there was a hole in the periodic table. But today, we can take element 42, molybdenum, and bombard it with neutrons, and we can make element 43 technetium. So much so that some of you may have ingested or had injected into you technetium. It's commonly used in medical imaging today. If you have ever had a radioactive tracer test, about 80% of all radioactive tracer tests today are done with technetium. So we use it in medical testing today, but for a long time, there was a hole here on the periodic table. So there are no holes left today, except you might argue, well, what about these big elements that scientists always seem to be coming up with new elements, all the way up to ununoctium up here on the periodic table? The thing about these giant elements down here is that we make them by smashing together smaller elements. And when we smash them together for a tiny fraction of a second, they come together and they form one of these larger, more massive elements. But all of these elements are so unstable that the vast majority of them decay in less than a second. So even if you make one of these atoms in one of these atom smashers, it's gone in less than a second. It disappears because it's so unstable, it decays into smaller atoms again. Even the most stable of these elements are not stable for much more than a second in time. So you can't really build a spaceship out of ununoctium or any of these heavy elements because they decay within a second. And so I would argue that you can't make anything in the universe out of any of this. So remarkably, our periodic table has on it everything that there is in the universe. If it's made of protons, neutrons, and electrons, it's on our periodic table. And if a UFO should ever land and explain all those things in astronomy that I'd love to know about that we haven't figured out yet, I can guarantee that if it's made out of protons, neutrons, and electrons, it's on our periodic table. So that raises the question, where did those protons, neutrons, and electrons come from in the first place? The stuff, the atoms that we're made of, are made of those fundamental building blocks. Where did they arise? And the answer is they came directly from the Big Bang. The next time you're getting up in the morning, the young students won't understand this, but those of us that are my age will understand this, and you swing out of bed and you're sitting there and you're feeling kind of old and creaky that day, regardless of how old you are, remember that the protons, the neutrons, and the electrons that make up your atoms are a lot older than you are. In fact, they date all the way back to the Big Bang, and they are, in fact, 13.7 billion years old. That number, the age of the universe, was determined about 10 years ago by a NASA satellite called the Wilkinson Microwave Anisotropy Probe. We'll see a picture from it here in a minute. And it's one of the hardest fought numbers in astronomy. We fought for 100 years to figure out the accurate age of the universe, and now we know it. It's 13.7 billion years old. And the protons, the neutrons, and the electrons in your body were made in the Big Bang. Now, the Big Bang isn't just a hypothetical idea that astronomers have come up with. The Big Bang can be directly tested in laboratories today. And in fact, this is a simulation of a collision at the Giant Particle Accelerator in CERN in Switzerland, on the border of France and Switzerland, where they take protons and they smash protons together at high speed, because when those two protons meet head on, the pressures and the temperatures and the densities in that collision are the same as they were a tiny fraction of a second after the Big Bang. Here on Earth, we can recreate the conditions of the Big Bang when we collide atoms like this in our atom smashers. And in fact, that's a large reason why we do it, is to make these kinds of conditions that we don't normally experience around us. So we understand the Big Bang fairly well. We know that during the Big Bang, the universe was really hot. and was so hot that the universe was filled with light, and that light consisted of high-energy photons, a kind of light called gamma rays. And every now and then, these two gamma rays would collide with one another, and when they collided with one another, they would make a piece of matter and a piece of antimatter. And the only difference between matter and antimatter is the charge. So this, for example, is a proton with a positive charge, and this is an antiproton with a negative charge. And so when these photons would collide, they would make two pieces of matter. And the only thing that was required for these two photons to make that matter was that they have enough energy. Einstein's famous equation, E equals mc squared, tells us how much energy it takes to make a certain amount of matter. If you know the mass of the proton and the mass of the antiproton, you can figure out how much energy it took to make them. And it turns out the only form of light that has enough energy to make these things are highly energetic gamma rays. Now, fortunately for you and me, gamma rays are pretty rare these days. Unless you work in one of the nuclear industries or work here at JLab, you probably don't encounter gamma rays very often. But in the early universe was filled with gamma rays. This was going on all the time. In the first few seconds of the universe, matter and antimatter were popping into existence as these photons would collide. The problem is matter and antimatter have opposite charges. And we'll remember that opposite charges attract one another. The positive proton and the antiproton are attracted, and they annihilate in a burst of energy, just like in Star Trek. When matter and antimatter come together, they annihilate, and you get back those two photons of light. If this was the only way to make matter in the universe, then every time we made a piece of matter, we'd make a piece of corresponding antimatter. But for reasons that physicists don't understand right now, every now and then in the early universe, the universe made a piece of matter, but it did not make the corresponding piece of antimatter. Or it made the antimatter, and the antimatter was so unstable that it decayed away, and all we're left with is the matter. But this is the matter, the protons that you and I are made of. They were made by light in the early universe, and those protons are the ones that remain because their partners either weren't created or decayed away long ago. The physicist or the scientist who answers the question about why the antimatter wasn't made sometimes or decayed away, without a doubt will win the Nobel Prize in physics. So my generation has been working really hard on figuring out this problem. We haven't gotten it yet, so maybe one of the students in here will finally be the person who figures out why it is that antimatter wasn't made and only matter was left over. Because today in our universe, there's essentially no antimatter, hardly any in the universe as a whole. Well, for the first few minutes in the Big Bang, the first 3 minutes, it was so hot that all the protons and the neutrons that were created start colliding with one another, and they start undergoing nuclear reactions. And neutrons and protons can collide to make a heavy form of hydrogen. And that heavy form of hydrogen can collide with neutrons to make an even heavier form of hydrogen. Or that can collide with a proton to make a form of helium. And this hydrogen and that proton can combine to make another form of helium. In the first 3 minutes of the Big Bang, the universe was hot enough that these protons and neutrons could collide with one another and start building up the elements on the periodic table of elements. And we get the formation of hydrogen atoms, which are easy because hydrogen atoms are just a single proton. But we get the formation of helium and lithium on the periodic table. But there's a problem in the first 3 minutes. The universe is rapidly expanding. It's expanding so fast, and it cools off so quickly that just 3 minutes after the Big Bang, the nuclear reactions shut down. It gets too cold for nuclear reactions. So the universe does not have a lot of time to make elements because it's only got 3 minutes of nuclear reactions to do that. On top of that, it turns out that just after lithium on the periodic table of elements, there's a bottleneck. The next element on up from lithium, the form of beryllium that would be made, is unstable. So unstable that the universe can't make it. This is what the periodic table of elements looks like today. This is what the periodic table of elements looked like 3 minutes after the Big Bang. There were only 3 elements in the whole universe: hydrogen, helium, and lithium. And I only include lithium here. There was a tiny, tiny amount of lithium in the early universe, so I include it here because there was some lithium made. But 3 minutes after the Big Bang, the universe was 75% hydrogen and 25% helium. There was no gold, there was no carbon, no nitrogen, no oxygen, nothing. I like to point out to students that chemistry class was a lot easier back then because there was just hydrogen and helium's a noble gas, so it doesn't underform molecules. The problem was there could be no chemistry class because there's no carbon and oxygen to make the chemists. Steve's webpage that has the periodic table of elements was a lot easier to build back then, but there could be no Steve to build it because there was no carbon or nitrogen or oxygen to make Steve. So that was the Big Bang in the first 3 minutes. So where did the gold come from? Because the gold didn't come from the Big Bang. The carbon and the oxygen in your body did not come from the Big Bang. So where did they come from? Well, we have to trace this hydrogen and helium gas over time and see what happens to it. So the next step after the Big Bang is that the universe continues to expand, and at first this gas is very evenly distributed, very smoothly distributed throughout the universe. But gravity starts clumping it together. And as gravity starts clumping this gas together, we can see clumps forming in the early universe. This is a picture of the glow left over from the Big Bang. This is a whole sky image. It's like one of those odd Earth maps where they try and show you the whole Earth map. So they disassemble the Earth and they spread the whole thing out. So this is a map that shows you the whole glow of the Big Bang over the whole sky. The light that you're seeing, it was taken by the Wilkinson Microwave Anisotropy Probe, that NASA satellite I mentioned a minute ago. And this is the glow. It was released 380,000 years after the Big Bang. But you'll notice that just 380,000 years after the Big Bang, matter is already clumping together. Gravity is already starting to pull it. And we can run simulations starting with a very smooth universe and just let gravity run in our simulations, and we can see how the universe starts gathering into clumps. And we go from the very smooth universe that we had early on to the very clumpy universe we have today. And any deep, deep image of the universe, like the extreme deep field that was recently released by the Hubble Space Telescope, the deepest image that humanity has ever taken of the universe, shows us that the universe today is very, very clumpy. The gas isn't evenly distributed, it's clumped together, and the basic building block of the universe is the galaxy. This is a picture of what our Milky Way galaxy would look like if we could get outside the galaxy. But as I said before, we've never been outside our galaxy. Our children will not get outside the galaxy, and their great-great-grandchildren will not get outside the galaxy because it would take hundreds of thousands of years to travel out to this distance to look back, even traveling at the speed of light. And we're a long way from doing that right now. So this is another galaxy, NGC 4414, that we think looks like our Milky Way galaxy. If we could get outside the Milky Way and look back on it, this is what our galaxy would look like. Our galaxy consists of a few 100 billion stars and giant clouds of gas and dust. And those giant clouds of gas and dust are where new stars are being born. Now, we don't see the Milky Way like this. We see the Milky Way like this because we live inside of it. It's like a giant pizza with a grapefruit at the middle. The grapefruit is this big bulge down here, and the pizza is the disk of material. But because we live inside the pizza, in the middle of the pizza, about halfway out from the center, when we look over towards the constellation of Sagittarius, we see the grapefruit down at the center, and then here's the rest of the pizza around us. Everything you can see in the night sky, with one exception, is part of our Milky Way galaxy. These stars are in the Milky Way. They just happen to be the stars that are above us. These stars are in the Milky Way. Those are the stars that are below us. These are the stars that are in the Milky Way that happen to be all around us. And of course, if you think about a thin pizza, if you live in the middle of the pizza, there's not much pizza above you, not much pizza below you, but lots of pizza around you, which is why our galaxy looks like a line cutting through the sky. In fact, the only thing that you can see with the naked eye that is not part of our galaxy is a faint fuzzy object in the constellation of Andromeda right here. And that faint fuzzy object is another galaxy called the Andromeda Galaxy, about 2.4 million light years away from us. And I'm going to guess that here in the Hampton area, you're not going to see that because of all the light pollution that you'll need to get out under dark country skies in order to see the Andromeda Galaxy. Inside of galaxies, the basic building block of the universe are stars. And stars are the next part of our story as what happens to the elements. Stars are giant balls of hydrogen and helium gas. Our sun is a giant ball of hydrogen and helium gas. It's about 300,000 times the mass of the Earth, It's 109 times the diameter of the Earth, so the Earth would be a little tiny spot up here compared to the size of the sun. But the sun has no solid surface. It is a gas all the way to the center. And it is, as I said earlier, 74% hydrogen, 25% helium, and 1% everything else. Down at the center of the sun, because of the weight of all these layers of gas pushing down on the center, as they push down on the center, they compress that gas. That gas is really hot down there. It's at a temperature of about 15 million degrees. And there are nuclear reactions going on down there, and that is what powers our sun. And there are two basic nuclear reactions in the universe. There are fission reactions, where you take big elements like uranium and you break them into krypton and barium and release a bunch of neutrons. Those are fission reactions. And there are fusion reactions, where you take light elements like hydrogen and collide them together to fuse or build bigger elements. Now, this one's important to us. Fission is important because this is how a lot of our electricity is generated. A fair bit of the electricity that's running the lights in this room and this projector are coming from nuclear power plants in Virginia. In central Virginia, we have the Lake Anna nuclear power station. And at Lake Anna, they're taking uranium atoms, they're splitting them apart, and in the process, it's releasing energy, and that energy is getting turned into electricity. We also make nuclear weapons out of this. Uranium bombs and plutonium bombs are fission weapons. Fusion, on the other hand, where you take the light elements and combine them to build bigger elements, is something that we have not yet mastered, at least for generating electricity. We have, however, mastered this, if you can call it mastering it, in nuclear weapons, hydrogen bombs. We can do this reaction in an uncontrolled way, but we haven't yet figured out how to control it and harness it and turn it into electricity. But we understand fission and fusion nuclear reactions quite well, and you can guess which one powers the sun, because I've already said that the sun is 74% hydrogen, and so the sun is made mostly of hydrogen, and it's fusion reactions that power the sun. Deep down inside the sun, in the core of the sun, but only in the core of the sun, not in the outer parts of the sun, just deep down in the core, it's hot enough, about 15 million degrees, where you can collide protons together and build up heavier elements. This is the set of nuclear reactions, the chain of reactions, that goes on deep down inside the center of the sun. What happens in the sun is a hydrogen atom, which is a single proton, which has a positive charge, and another hydrogen atom, a single proton with a positive charge, collide with one another. Now, they don't want to come together because, remember, like charges repel one another. So a positively charged proton and a positively charged proton, normally when you try and drive them together, both positive charges will repel one another and they'll pull apart. But if you do this under high enough temperatures, like the 15 million degrees that we have down at the center of the sun, you can drive them together so forcefully that they get so close together that the two of them can react and form something heavier, a form of heavy hydrogen. And that heavy hydrogen can combine with another proton to make a form of helium. Two of those combine to make another form of helium. The ultimate result in our sun is that 4 hydrogen atoms go in and 1 helium atom comes out. So hydrogen is converted to helium in our sun. Each and every second inside of our sun, 600 million tons of hydrogen are being converted to helium in our sun every second. Now, you remember from chemistry class in school that in chemical reactions, mass is conserved. If you start with a certain amount of mass to begin with, that mass has to be conserved. That's no longer true with nuclear reactions. In the case of nuclear reactions, it's the combination of mass and energy that are conserved. This helium atom that comes out has less mass than the 4 hydrogen atoms that went in. It's a tiny fraction. It's 0.7% less mass than the 4 hydrogen atoms that went in, but that 0.7% of matter was turned into energy. And according to Einstein's E equals mc squared, that matter that went missing comes out in the form of energy, and that is what powers the sun. So our sun is converting hydrogen to helium. Now, this is a problem for our sun, or at least the long-term future for our sun, because our sun is like your automobile. It's running on fuel, and someday our sun will run out of fuel. This shows what our sun looked like when it was born. This is the distance from the center of the sun out to the surface of the sun. This is the composition of the sun. So this is the core, This is the surface, and you can see that throughout the sun, when it was born at birth, the sun was mostly hydrogen and a little bit of helium. Today, the sun is 4.5 billion years old, so it's about halfway through its life. The sun has used about half of the hydrogen in its core and converted that to helium. Our sun is about halfway through its life. It is a middle-aged star. When the sun is about 10 billion years old, it will have converted almost all of its hydrogen into helium. And at this point, our sun will start to die because there will be no longer any nuclear reactions going on down at the center. And our sun needs those nuclear reactions because gravity is trying to pull all that gas together. And the nuclear reactions are providing the force that balances against the force of gravity. Without those nuclear reactions, gravity will win, and the center of our sun will start to contract. And as the center of our sun contracts, it releases so much energy that it puffs up the outer layers of the sun into a red giant star. So the ultimate fate of our sun is to become a red giant star. This is the size of our sun today. This is the size of our sun when it's a red giant star. It will get enormous compared to its size today. But what's contradictory about it is the center of our sun is actually shrinking. The center is shrinking and getting smaller, and the outer layers are getting puffed out. And in fact, that center will eventually become unstable, and when it becomes unstable, it will blow off those outer layers. In its lifetime, our sun is converting hydrogen to helium. When it's a red giant star, at the end of its life, that core will get hot enough that it can actually convert helium atoms into carbon and some carbon into oxygen on the periodic table. It can only do that later on because right now it's not hot enough at the center of the sun to convert helium into carbon. The problem with helium is it has 2 protons. Another helium atom has 2 protons. That's +2 and +2. It's a lot harder to drive those together. Whereas it takes a temperature of about 10 million degrees to fuse hydrogen to helium, the temperature has to be over 100 million degrees to fuse helium into carbon. And our sun's not hot enough yet. But it will be in the red giant phase, and it will fuse helium into carbon and a little bit of carbon into oxygen. But our sun isn't big enough, and it won't do any more than that. And that's as far on the periodic table as our elements will go. Now keep in mind that the carbon, the nitrogen, and the oxygen in your body did not come from our sun, because our sun won't do this until it's dying. So it's not as if it did this long ago. This is what the sun's going to do at the end of its life. And this is what's going to end up. This is the ultimate fate of our sun. This little white dot at the middle is a white dwarf star. It's the burned out core of a star like our sun. And this beautiful planetary nebula that you see around it, this glowing nebula, is the outer atmosphere of the star. The dead core becomes unstable and it puffs off those outer layers and creates this beautiful planetary nebula right there. The other problem with stars like our sun is all the carbon, the nitrogen, and the oxygen, it stays locked up in that white dwarf star. It doesn't return those elements back out into space to be used by future generations of stars. So the carbon, the nitrogen, the oxygen in your body did not come from a star like our sun. The carbon, the nitrogen, the oxygen in your body actually came from a much bigger star. Giant stars undergo different nuclear reactions. And so let's talk for a minute about the nuclear reactions that happen in big, giant, massive stars. And this is a really cool plot that shows you how much there is of each element in the universe. This tells you the amount of the element, and this is each of the elements listed here. And the thing to know about this table is this is a logarithmic table, which means each one of these tick marks is a factor of 10. So just looking at this, it looks like there's almost as much nitrogen as oxygen in the universe, but in fact they're separated by about 1 tick mark, which means there's 10 times as much oxygen as there is nitrogen in the universe. So these are the abundances of the elements. And we've already said that hydrogen and helium are the most abundant elements by a lot in the universe. And then there's hardly any lithium, beryllium, and boron, but here are the other elements. And if you look at that periodic table of elements, you'll notice something very interesting about the abundant elements. So can someone tell me what atomic number carbon is? 6. So what number is oxygen? 8. What's neon? 10. Magnesium? 12. Silicon? 14. Do you see a pattern developing here? It's the even-numbered elements. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. The even-numbered elements in the universe are 10 times more abundant than the odd-numbered elements. Why is that? Why does the universe prefer the even-numbered elements over the odd-numbered elements? By the way, another thing before we go on to point out about this table is I mentioned that hydrogen and helium are the most abundant. Look at what the third most abundant element in the universe is. It's oxygen. You're made of oxygen. You are made of the third most abundant element in the universe. After oxygen, you're made mostly of carbon. Carbon is the fourth most abundant element in the universe. You are made of the common stuff of the universe. Carbon and oxygen are not rare. After hydrogen and helium, they're the two most abundant things in the whole universe. So let's go back to this question of the even-numbered elements. What is it about the even-numbered elements? It has to do with the way massive stars live out their lives. Massive stars can fuse hydrogen to helium. But when they're done fusing hydrogen to helium, they can fuse helium to carbon. And then they can undergo other nuclear reactions where helium and carbon can make oxygen. Helium and oxygen can make neon. Carbon and carbon can make magnesium. Oxygen and oxygen can make silicon. And if you look at these reactions, you'll notice that the basic building block of all of them is the helium atom. 3 helium atoms make carbon. Helium and carbon make oxygen. Since the basic building block of all the elements is the helium atom with number 2, if you start with a building block that's 2, and you put 2 of them together, you get 4, 6, 8, 10, 12, 14, 16. The way massive stars live out their lives is they fuse ever heavier elements, and they're always using helium. So silicon and helium make sulfur, plus helium makes argon, plus helium makes calcium, and on up the periodic table until we reach iron on the periodic table. Massive stars in their lives will fuse hydrogen all the way up to iron on the periodic table. So this is the periodic table today. This is what massive stars can do. During their lives, they'll fuse hydrogen to helium, helium to carbon, carbon to oxygen to neon, to magnesium, to silicon, sulfur, argon, all the way up to iron. But iron's really special. Turns out iron is the most stable element in the universe. There's no element that's more stable than iron. That is, iron is so tightly held together that if you fuse these atoms to make iron, it releases energy. If you fission these atoms, break them apart to get down to iron, you release energy. But when you get to iron, there's no place else to go. If you wanted to take iron and build up heavier elements, you would have to add energy. And stars don't want to do that. Stars are using these nuclear reactions to generate energy. Having to do nuclear reactions where you have to put energy in will just suck energy out of the center of the star. So stars end up here at iron. And in fact, a massive star, a really big star, say a star that's about 25 times the mass of our sun, it will fuse hydrogen to helium for about 7 million years. Our sun will do that for 10 billion years. Really massive stars, even though they have a lot more fuel available to them, they don't live very long lives because they burn that fuel so fast. It'll burn helium to carbon for 500,000 years, carbon to neon for 600 years, neon to oxygen for about a year, oxygen to silicon for about half of a year, 6 months, and then silicon to iron in 1 day. In the very last day of the life of this star, it starts fusing silicon into iron. And in the last few minutes of that star's life, the inside of the star looks like a giant onion. There's a big ball of iron sitting down here at the middle, and surrounding that is a shell of silicon that's fusing to iron. And around that is a shell of oxygen fusing to silicon, and on out. As I said, this iron is so stable, it can't undergo any nuclear reactions. So without nuclear reactions, gravity is pulling that ball of iron together. Gravity is trying to contract it. The iron atoms are pushing back against the force of gravity. In particular, it's the electrons that are in there that are pushing back. But gravity squeezes it tighter and tighter, and they're pushing back further and further. Eventually, though, this silicon shell keeps dumping more and more and more iron on that core. And that core gets more and more massive and more massive. And eventually it gets so massive and the gravity is so strong that the atoms can't push back against the force of gravity anymore, and they give up and the core collapses. And in about 2 seconds, the core of this star, which is about the same size as our planet, but weighs probably 2 or 3 times the mass of our sun, So it's many, many times the mass of the Earth, but about the size of the Earth. That core collapses. And when it collapses, it releases so much energy that the star blows itself apart in a titanic explosion called a supernova. Only the most massive stars go supernova. If you look in here, this is in a nearby galaxy called the Large Magellanic Cloud. This is a giant star-forming region right here. There is a star in this picture that is about to go supernova. It went supernova in 1987. This was a picture taken a couple days before the star blew itself up. If looking at that picture, can you find the star that's ready to blow itself up? If you could, you're doing a lot better than astronomers did, because we had no idea that it was that star right there that was ready to blow itself up. So if I go back, you can see the star. See, the thing is, with astronomy, we can see the surface of a star, but we can't see what's going on deep down inside the star. So we had no idea that that star was ready to blow itself up. But for a few days, that star outshone our whole Milky Way galaxy of hundreds of billions of stars. That's how much energy they give off. And when these stars explode, the majority of the mass of the star is blown out into space. And all the elements that were made during the life of that star are spread back out into space as well. So we had said that this is the periodic table of elements. This is what it looked like 3 minutes after the Big Bang. This is what it looks like because of stars like the sun. Massive stars can build all the way up to iron, and because they blow themselves up at the end of their lives, they return all these elements back out into space. But remember that core collapse where that big ball of iron collapsed on itself in 2 seconds? When that big ball of iron collapses, the densities and the pressures and the temperatures are so high that in about 2 seconds, all the other elements on the periodic table are made. The reason that gold is precious to us is because it's rare. And the reason that gold is rare is that the universe had about 2 seconds to make it when the core of that star collapsed. Because that's the only time that the pressures, the temperatures, the densities are high enough to make some of these heavy elements like gold and mercury and silver. They're made when these massive stars implode at the end of their lives. So let's trace the history of your atoms, and in particular your gold atoms, from the very beginning of the universe until the present day. The atoms in your gold jewelry started out as hydrogen and helium atoms in one of these giant star-forming regions, like this one, this giant cluster of stars. The first time your atoms found themselves inside of a star, they weren't deep down in the core of the star. They were likely in the outer parts of the star. And remember, there are no nuclear reactions in the outer parts of a star. The nuclear reactions are only in the core of the star. So the first time your atoms found themselves inside of a star, that star exploded in a titanic explosion, and it blew those atoms back out into space, but they were still hydrogen and helium atoms. The second time your atoms found themselves in one of these giant star-forming regions, like the Orion Nebula. Here's the belt of Orion and his sword, and that's the Orion Nebula, a giant star-forming region. The second time they found themselves in a star, they likely found themselves not deep down in the core of the star, but in the outer layers of the star. And when that star blew up, it returned all those elements back out into space. The third time your atoms found themselves in one of these giant star-forming regions, it's likely that they found themselves deep down inside the core of the star. And this time, the hydrogen atoms were converted to helium, the helium to carbon, the carbon to oxygen, all the way up to silicon, up to iron. And then when it exploded, it made the gold that's in your jewelry. And that gold was spread back out into space in that titanic explosion at the end of the life of the star. After that gas spread out into space, your atoms found themselves in one final star-forming region, like the Eagle Nebula down in Sagittarius, the famous one with these beautiful pillars of dust sticking up. And this is really neat to astronomers because we actually see little clumps of gas up here, and those little clumps of gas are forming stars. And when we look at those forming stars, this particular group of stars comes out of the Orion Nebula. We see the stars, and we see surrounding them these black disks of dust. Those are planets in the process of forming. The last time you were in one of these star-forming regions, your atoms were not in the star. They were in that disk of dust surrounding the star. And as gravity clumped those pieces of dust together, they made little rocks. Those rocks clump together to make asteroids. Those asteroids clump together to make planets. And the fourth time that your atoms were in a star-forming region, they ended up not in the star, but in the third planet from the sun. And they weren't deep down inside the Earth. They were actually up close to the surface. Your atoms have spent most of their time up close to the surface of the Earth here. And that is where your atoms have come from. You are, as Carl Sagan said, literally made of star stuff. The atoms in your body were forged in the furnaces of stars billions of years ago. But your atoms haven't been in just one star. You've probably been in at least 2 or 3 different stars in the history of the universe. And as I said, this time, your atoms ended up not in the star, but in the planet. The last thought I want you to leave you with is, what is the ultimate fate for your atoms? So you're made mostly of oxygen. What's going to happen to your atoms in the future? Because I hate to tell you, you don't own your atoms. You're just borrowing them for the time that you're here on Earth. Well, when we all pass away, whether we're cremated or buried, our atoms become part of the surface of the Earth. And over millions of years, those atoms will be recycled through plants, through animals, through other living things on the surface. Eventually, though, our sun will die. When our sun dies, it will become a red giant. And our star will get so big, the diameter here is 2 astronomical units, which means the radius is 1 astronomical unit. An astronomical unit is the distance from the Earth to the sun. Our sun will get so big that the outer layers of the sun will come all the way out to the Earth's orbit around the sun. When it does that, it may not be enough to completely vaporize the Earth, but it will vaporize the outer layers of the Earth. So your atoms, which are part of the outer layers of the Earth, will be vaporized off the surface. They will become part of the outer layers of this red giant star. And when it dies, our sun, you'll remember, the core shrinks down to make a white dwarf. The outer layers are blown into a beautiful planetary nebula. That is the fate of your atoms. You will someday be a planetary nebula. And I didn't mention it before, but I'll mention it now. See that green glow that's coming from the center of the nebula? Those are oxygen atoms. So those are the oxygen atoms that you are made of, and that's where you're headed someday, is you will be back out in space, and then after billions of years into the future, these atoms will be in the next generation of stars. So the Milky Way is like a giant recycler. Your atoms have been in stars, and they will be in future stars again, but you have them just for this short period of time. So thank you very much. I'm happy to take questions for a few minutes. I think we have about 5 minutes for questions, so thank you. Yes?
Does the city of Charlottesville have a black sky at any point in time? Is there no prohibited anywhere else?
No, Charlottesville does not have a dark sky ordinance, not a very good dark sky ordinance anyhow. I don't know that there's too much hope for getting it in Virginia. And I think really we're just going to have to work in rural areas and try very hard to preserve the dark skies that we have in the rural areas today. But I'm not holding out much hope that there's any hope for taking cities like Charlottesville or Hampton and trying to reverse what we've already done. So, and we have worked, actually, I will say we've worked very hard in Charlottesville to try and get a dark sky ordinance, but there's just too much pushback from others. So, yes? Yeah, so the middle of the Milky Way, the grapefruit of the middle, it's a big ball of stars called the galactic bulge. And those were some of the first stars to form when our galaxy was forming. And so if you look at it in that picture, it's just a big ball of stars sitting down there at the center of the galaxy. Really old stars. Yes? Okay, so the question is, how do we know that when we look at things that are far away, like millions of light years away, how do we know there's not a black hole between us or other objects? Well, the answer is in many cases there are other objects between us, and we see those. So let me go back to these. So when we look at star-forming regions like this, most of the stars that you can see here are actually foreground stars that are in the foreground. The thing to keep in mind about black holes is they are incredibly small. If we take our sun and shrink it down till it's a black hole, its radius is just a couple kilometers, which is a couple miles across. So that is so infinitesimally small when we talk about distances that are this big that it has no effect at all. So, well, see, that's the thing. Black holes, they have this really bad reputation of sucking everything into them. And it turns out it's only if you get right up close to them that they suck everything in. But an interesting thing to think about our sun is the Earth is held in orbit by the mass of our sun. If we took our sun and shrunk it so small that it became a black hole, it turns out we haven't changed the mass of the sun, and we haven't changed the distance from the Earth to the sun. So even if our sun were to turn into a black hole, the Earth would continue to orbit the sun just like it does today. So it doesn't suck things in. The only way that black holes suck things in is if you get really, really close to them, close to what's called their event horizon, where gravity is very strong. But that event horizon is the thing that's just a couple miles across. So you have to get really close to black holes. Yes? So there are two things there. One is, do black holes strip matter off stars? That yes, stars are often born in binary systems, two stars orbiting around one another. And in those binary systems, if the more massive one dies and becomes a black hole, when the less massive one dies and becomes a red giant, that matter can get sucked into the black hole. There's a beautiful example of this in the constellation of Cygnus. It's the best candidate we have for a black hole. But isolated stars like our sun, which are not in binary systems, black holes are not at all common in the galaxy. It is not common, I would say, in fact, it's remarkably unusual for an isolated star like our sun to have an interaction with a black hole. And the only really massive black hole in our galaxy is deep down at the center of the galaxy. Down at the center of our Milky Way galaxy, there's a black hole 4 million times the mass of our sun. But that's 26,000 light years away from us, and we orbit around the galaxy. We never find ourselves down there in the center. The only stars that have to worry about that black hole are the ones that are close to it. So,
we thank Dr. Murphy again, please, for
thank you.